Okay. So thank you so much. I'm going to give a short talk on Hom-Lie structures on three-dimensional skew-symmetric algebras. And my name is Elvice Ongong'a from Melody University. So I will just start with some preliminary definitions. So Hom-Lie algebras are simply a generalization of the Lie algebras, and this first appeared in this article by Hartwig, Larsson, and Silvestrov. And when they were studying some deformations of Lie algebras using sigma derivations. And so we have a generalized Jacobi identity, which is called a Hom-Jacobi identity. So a Hom-Lie algebra is simply a vector space endowed with a Lie bracket, which is a bilinear map, and a Lie linear map, which is always called a twist in this case, that satisfies skew-symmetry in condition 1, and condition 2, which is called Hom-Jacobi identity. So when we have alpha as an identity map, we end up with the usual Lie algebra case. So this talk is focusing on such linear maps or such linear twists that convert any skew-symmetric algebra into a Hom-Lie algebra. And the usual question is that, are we always sure that for any skew-symmetric algebra, you can always be guaranteed to get a non-trivial alpha that can turn it into Hom-Lie algebra? So the space of such linear endomorphisms or such alpha that turn any skew-symmetric algebra into a Hom-Lie algebra is referred to as Hom-Lie structures. Yes, so the main part of this talk is concerning three-dimensional Hom-Lie algebras, which is published in paper 2, given in the footnote below. So first, we'll want to say what we mean by these structure constants. So if you go to an n-dimensional vector space with basis elements E1 to En, we can associate structure constants to the bilinear map, which we denote by thisCijs, and to the linear twist map alpha, which we denote by these Aits. So they are simply parameters in the linear expressions in terms of this basis for each map. So it happens that we can rewrite the Hom-Jacobi identity here using these structure constants. And so if we substitute this equation 3 and 4, we end up with a general a system of polynomial equations given by 5. And these structure constants also follow from skew-symmetry, so that if you interchange the position of I and j, you get a negative. And if I is equal to j, such a term becomes 0, since we are working on a field of characteristics 0 and algebraically closed as well. So the idea is that, of course, equation 5, we have more generally like cubic polynomial equations, but we want to write them as linear in one of these parameters from alpha. So we write them as linear in these Aits, and we have this equation 6. And so we can represent such an equation in matricial form. If you have these Aits represented by a column matrix alpha, and then you have the other terms remaining are written out as matrix M, so that MA alpha is 0 simply from this equation 6. So M has these elements as sums of these C's, and A alpha is simply the column matrix involving the columns of alpha, like a vec of alpha. So M has n squared columns, since we always have n squared elements in alpha, and it has n choose 3 by n rows. since this is the number of equations we get by taking 3 basis elements at a time in the Hom-Jacobi identity, and we have n times this because we have n elements when we write out the equations. So in 3-dimensional case, where I said we are focusing on in this talk, M is a 3×9 matrix, and its elements inside look like this. For the first column, for the second column, all the way to the 9th column, they are simply sums in these structure constants. And if you look at M, therefore, it represents a linear map which you denote by L. And therefore, for us to realize a Hom-Lie algebra with an untrivial alpha, then we expect a alpha to lie in the kernel as well. And using the nullity rank theorem, it means that we can bound the dimension of the possible solutions of alpha. Maximum, of course, it can be 9. And with this, the minimum, it can be 6 because the maximum rank of M can be 3. And this therefore led to this result given by Rem and Gose, that indeed all 3-dimensional skew-symmetric algebras are really Hom-Lie algebras. This means that if you get any skew-symmetric algebra that is 3-dimensional, you can get the space of alphas. There is always alpha that can turn it into a Hom-Lie, and this alpha is non-trivial. So in our results, we find some correspondence. What we are going to show that actually, if I write out a matrix C, simply a matrix of these structures, these are in the first row, these are structures relating to E1 and E2. In the second row, E1 and E3, and the last row, E2 and E3. There is a correspondence between the rank of this matrix C and the dimension of the Hom-Lie structures in 3 dimensions. And we are going therefore to investigate what happens when we move from the minimum dimension to the maximum dimension 9. So dimension 6, 7, 8, and 9. So we get some nice correspondence that the rank of C kind of corresponds to this dimension by indeed connecting the rank of C and the rank of M. So as you can see clearly, M is this nearly complicated, it has sums of CIs and all that, but C is simply a simple matrix gotten from the structures of the skew-symmetric algebra. So the first result is that when C is of full rank, then this is the only time that we achieve the minimum dimension. This is the only time that the dimension of such Hom-Lie mu is 6. And this happens if and only if the determinant of C is non-zero. So that is C is of full rank. And an idea of the proof is that if you write out all the 3×3 subdeterminants of M, they end up being factored as they end up having the determinant of C as a common factor. So there are around 84 such expressions, and all non-zero expressions, they have determinant C as a factor. So this correspondence again continues when we go a little lower in the ranks, and the rank of C, when the rank of C is 2, we also find out that the dimension of the Hom-Lie structure is 7. This is the reason from the previous theorem. We have said that if C is of full rank, then the dimension is 6. And if C is not full rank, then the dimension cannot be 6. That means it can be 7 or more. And so again, we compute all the 2×2 subdeterminants of M, and we find out that they are also having the 2×2 subdeterminants of C as either common factors in some linear expression. And so in a way, there is a connection between the rank of M and the rank of C, again, when M is of rank 2. And then this tells us indeed, when M is of rank 2, therefore, the dimension of Hom-Lie structure is 7. So every possible way for C to be rank 2, we rewrite out all these, we look at all possible cases when rows are maybe linearly independent, or when some rows are 0. And in our list of these 2×2 subdeterminants of M, we find that indeed the rank of M is 2. in that case. But in the next session, this correspondence fails in this sense. Probably you could have expected that again, when the rank of C drops further, we only get the dimension to be 8. But it happens that in this case, when the rank of C drops to 1, then you can either have the dimension either being 8 of the Hom-Lie structure, or it can be full, the maximum 9. So we just give the possible cases. When the dimension of the Hom-Lie structure is 8, this is the case when we have this as a matrix C such that everywhere else is 0 except in one place, non-zero, in every other possible case except in the secondary diagonal. So we can have these structures everywhere else except in the second diagonal. So we have 6 cases. So the next part is the cases when we have this maximum. So the rank of C is 1, but we can get a maximum dimension 9. And this is a case, as I will be giving an example, say of the Lie algebra, Heisenberg-Lie algebra. If you have this as zeros and this C1, 2, 3 as 1, that is the case of the Heisenberg-Lie algebra. And you can always have any alpha to turn this Lie algebra into a Hom-Lie algebra, and therefore it means you can achieve the maximum dimension as 9. So we have these 5 cases in this when rank C is 1. And we have an interesting also result here that if you have 2 skew-symmetric algebras, so is their Hom-Lie structure. So if Hom-Lie mu is the Hom-Lie structure of L and Hom-Lie mu bar is the Hom-Lie structure of L bar, then their Hom-Lie structures are also isomorphic. So this means that 2 isomorphic skew-symmetric algebras, they have their Hom-Lie structures having the same dimension. So this proposition is important. It means that you only need to study the representatives of such skew-symmetric algebras, and you can say something about the dimension of the Hom-Lie structures in each of the family represented by these representatives. So just to give examples, even as I finish up, one example is this Heisenberg-Lie algebra. So if you write out C, so you have the last structure as 1 and the other structures as 0. And this, according to what we had before, this is falling in the category when the dimension Hom-Lie is 9. And if you have another, just to illustrate the proposition, if you have another Hom-Lie algebra, another Lie algebra that is isomorphic to this Heisenberg-Lie algebra, its C looks like this, it's of rank 1. And again, its dimension is the same. So there are isomorphic algebras and the dimension of the Hom-Lie structures are the same. So these are already in the classes that we gave earlier, C3 and C1. The final part, the only time we get this, an example for the minimum dimension of the Hom-Lie structures, is when you consider the simple Lie algebra. So in this case, you get C of full rank, it's of determinant 4, which stands 0. And indeed, if you compute further, you'll get that alpha in general looks like this, with 6 free parameters that you can choose freely over C. So the dimension of such Hom-Lie structures for the simple Lie algebra is 6. So thank you so much. That's my talk. A few references that I'd mentioned through my talk. Thank you.